really just want to sort of make the point of, we don't need to understand this in detail, but we do need to understand enough of this so that it makes sense when we apply it to the periodic table, because you will see that this explains the chemistry of the periodic table so beautifully that that's one of the reasons why I like teaching it so much. It's very elegant. And one of the things you find out about science is that if something is elegant, it's generally right. Meaning if something is simple in its in its elegance, if it explains something simply, generally that tends to be the case. That makes the most sense in the long run. So I'm going to sort of go back a little bit and see where this whole idea started. And if you remember, it kind of started, here we go. When we were looking at different colors being emitted from elements when they're excited. And they're, in this instance, they're being excited by energy from the flame. So it was noticed, it's been known for a long time, that different elements burn with different colors. That's how fireworks work. You paint fireworks with different salts, barium salts, lithium salts, potassium salts, rubidium salts, calcium salts. When they explode, they have different colors. So that's been known for a long time. And what we have to remember, excuse me, what we have to remember is that this is light being emitted from the atom. So this is light coming from the atom towards us. And remember, this is only a tiny fraction of the light that's being emitted that we can see. Yes.
Is it the same color for like copper 2 and copper 1?
No.
Okay.
No. Because the electrons, there's a different number of electrons. And so it's going to look slightly different.
Okay.
You may not be able to see it, but if you looked at it, if you took all those wavelengths and broke them down into the individual spectra, you'd be able to tell the difference. You may not be able to see it visually. So this is light being emitted from the atom. And because they're different colors, we know that they're different wavelengths. And because they're different wavelengths, we know that they're different energies. And that is the key to the whole thing, is different light, different colors mean different frequencies or wavelengths, same thing. And that means different energy. And so when we look at the light coming off of an excited atom, and in this case, we're looking at hydrogen, you can split that light into a whole bunch of different particular wavelengths. And we know that Niels Bohr came along and looked at these different wavelengths and made sense of it. Now, at the time, right at the time of Bohr, people were trying to make sense of this using what I call, classical or Newtonian physics. Basically, Isaac Newton, Isaac Newton showed how gravity. He didn't know how gravity worked, but he demonstrated it with a lot of equations showing exactly how the Earth rotates around the sun, and there's a particular amount of energy, and had all these equations, and they made perfect sense. So people are trying to do the same thing. Well, if it's true for the solar system, it must be true for the atom too, right? You've got electrons moving around the nucleus, much like planets going around the sun. We'll just use Newton's laws and figure out what these energies are. But that doesn't work, unfortunately. Why it doesn't work is because, the first part of it works. You've got the nucleus in the middle, just like the sun, very, very dense, has a lot of mass, okay? And then, but the difference is the nucleus is charged, and the electrons going around are charged as well. And so you have a positive charge in the middle, and you have negative charges going around the outside. Now, unfortunately, that is slightly different from the case of the solar system, where everybody basically has the same charge. And so the problem with that is, since you have moving charged particles, they're supposed to give off energy as they move, much like, you push a car down a road. It's supposed to give off energy. It's not going to move forever, right? It's going to be giving off energy as it moves. So electrons, as they move around the nucleus, should constantly be giving off energy. And as they're constantly giving off energy, they should be losing energy and moving closer and closer and closer to the nucleus. So two things should happen. The atom should constantly be glowing because it's releasing energy, and that energy would be just white light, because all these electrons would be all over the place. They'd be here, they'd be here, they'd be there, they'd be here. They'd be in all sorts of different places and moving down different places. So it should have all kinds of different wavelengths. So it should be just a complete mishmash of different frequencies. And as the electrons lost energy and moved closer and closer and closer to the nucleus, it should just crash into it and they should collapse. Neither one of these things happens. We don't see white light coming from atoms. We see particular colors. And as far as I know, not all atoms in the universe are collapsing in on themselves. I don't think. That hasn't happened yet. It might happen someday. So that's a problem. That means that this way that the chemists and physicists have been looking at the universe for like hundreds of years doesn't work for this particular system. So good old Niels came along and said, the only way that I can work out how this makes any sense is if, instead of electrons being anywhere, just moving all over the place, they're in very fixed positions. 1, 2, 3, 4, moving further and further from the nucleus. And so he thought that as the atom received energy, as you excited the atom, the electron would move from the ground state, we call it the ground state, up to excited state. So it would go from 1 to 2 to 3 to 4. And he actually measured the distances. He figured out what the distance must be for each of these places far from the nucleus, based on the energy of the light that the hydrogen atom emits. Because you remember, the energy of light depends on Planck's constant and the wavelength. So, man, I'm having a hard time this morning. So the energy of each individual wavelength is equal to Planck's constant, and you're not going to need to remember Planck's constant, and the frequency. So he took all of those different energies, he calculated all those energies from all those different light sources, and then figured out, and remember, this is before supercomputers or really even calculators, figured out what those distances must be. And it turned out that he could plug in all these distances that he worked out and relate every single wavelength of light that came from hydrogen. So it's like, yay, Niels has figured it out. It explained a lot of different things. It explained why atoms emitted light in fixed wavelengths, because they go from one fixed place to another. They move from 4 to 3, they move from 4 to 2, they move from 6 down to 1. And the further they fall, the more energy they give off, a different color. It's like, oh man, Niels, you're the man. And of course, he got the Nobel Prize in physics, and he's a national hero in Denmark. So, hydrogen atom. Remember, this is only the hydrogen atom he was looking at. Has certain energy levels. So these are energy levels for electrons. I want to make that clear. This does not involve the nucleus. These are all electrons, because chemistry is all electrons. So he called these stationary states, these different distances from the nucleus. Each one has a different circular orbit. So if this is, oops, let me go back. So if this is the nucleus, and then we have electrons going around, he would say this would be 1, and then that would be 2, and then further away would be 3. And so there'd be these fixed distances that these electrons could move. The higher the level, the further away the electron is. So it takes more energy to push that electron away from the nucleus. Because remember, protons and electrons attract each other, right? So it takes energy to push them further apart. And then when they come close, when the atom relaxes and the electron comes back closer to the nucleus, that releases energy. Now it's more stable. So it releases energy in the form of that light. So when the hydrogen electron is in the first lowest state, that's called the ground state. And when it's in the ground state, it's not releasing any energy. It's quiet. There's no light. It's not absorbing any energy. It's not releasing any energy, which is different from the sort of classical model being, I've got a charged particle going around another charged particle. That's got to be releasing energy all the time. And Bohr said, no, it doesn't. That's the stable ground state of the atom. And so that, that was released with much fanfare and yay, hooray, we figured everything out. So the atom doesn't radiate energy in its stationary state. So we don't see white light coming off of it. And we don't see, we see very specific wavelengths depending on the energy difference between these different states further and further away from the nucleus. So an electron is in any orbit higher than the first one, we say it's excited. It could be 1, 2, 3, 4, however far away it is. And then when it falls back to the ground state, as I mentioned, it releases that light, that photon of light of a very specific energy related to the distance that it came falling back down again. What does this all mean? So you excite an electron, moves further away. The electron relaxes, comes back down, releases energy. So it absorbs energy as it moves further away and then releases energy as it comes back. So, and then you can tell basically where it's fallen back from based on the wavelength. If it fell far, it's going to be a high energy photon it releases. If it falls only a little bit, it's going to be weaker energy. And that explained why some of the light was in infrared and some was ultraviolet and some was in between. Okay? So this is basically how we look at it. This is called a transition diagram. And it just sort of shows you in a very simple fashion where the energy goes in and where it comes out. So we generally, at most of the time, we're going to find the electron here at the ground state. It's not getting any energy coming in. It's not releasing any energy. It's staying there. And that's the lowest it can be. It can't move any closer to the nucleus or it'll collapse. So it stays at this level. If we do something to it, if we heat it up or we put electricity through it or we excite it in some way by adding energy, it moves up. So now this electron, let's say, is at the third level. It's further away. So it absorbed a specific amount of energy to get it there. So this is important too. So this would be absorption. We would call this part absorption. And we can also look at the absorption spectra as well. This is how scientists determine that there's particular molecules like on the sun or on a distant planet. If it absorbs specific wavelengths of light, that tells you how how much energy it absorbs for the electrons to get excited. Its emission spectra, looking at the light it actually gives off, tells you how far away the electrons are when they come back to the ground state. So it's absorption, getting energy in, and electrons going up, and then emission as the electrons give off light and the electrons fall back down to the ground state. That's the difference.
Excuse me?
Yes.
Why is the distance between the two levels are different? Is that drawn to scale or not?
No.
Okay.
No. We'll find it. We'll find out as we move further and further away. The difference in energy between these states gets smaller and smaller and smaller. That becomes really important later on.
Okay.
When we start breaking down, because we'll find out that this particular model is not sufficient to explain everything else other than hydrogen. Unfortunately, it works perfectly for hydrogen, but we'll learn it doesn't work for anything else. So that's kind of a problem. So think of it as like a staircase. So you walk up the stairs, you give off energy, you're putting energy into moving up the stairs. But then if you have a ball and you just roll it down the stairs, that's releasing energy. So we take energy to push the electron further away, and that's not how you spell absorption. I don't know whoever, I grabbed this from someone who can't spell. So absorption is the energy going into the atom, and emission is the energy coming back out. So as the atom relaxes from excited state to ground state, it emits energy as the ball goes down the staircase. And then we push the electron up the staircase by absorbing energy, okay? So 1 being the lowest, and then 2, 3, 4, 5. And notice, as Raymond pointed out, the difference in energy as you go up gets smaller and smaller and smaller. Once you get up to like 6 or 7, the difference in energy is really, really small. And this shows you how, yes, Nicholas.
So does that mean as it gains more energy, it's easier to gain more energy? Does that make sense? Like,
I don't know quite what you mean by that.
so since the levels are closer together, is it easier for it to jump to that next level than what it'd be when it's closer?
Oh, it doesn't take, yeah, I mean, it doesn't take as much energy. Yeah, it takes much more energy to move something from the ground state to the first excited state than it does to move it to the 3rd, 4th, 5th, or 6th. Those are like really small differences in energy. Yeah. So this is how Bohr worked all this goodness out. So we have the nucleus in the middle here, and he worked out how far these different levels would have to be from the nucleus to explain all these different lines. So over here on the right side, we can see that as you move further and further up, as we mentioned, the distance, the difference gets smaller and smaller and smaller. So there's a big jump from 1 to 2, and then a smaller jump from 2 to 3, and then smaller from 3 to 4, and then it gets smaller and smaller and smaller. But as you fall back, so if you fall back from these really high levels to one just below it, that's a really small amount of energy. That's infrared light. Remember, infrared doesn't have as much energy as all the other colors plus ultraviolet. So going from a high level to another slightly lower level releases just a little bit of energy. And those are the infrared series. So moving from 7 to 6 and 6 to 5 and 5 to 4 and 4 to 3. Those are small differences with not much energy. So those would be infrared. So those would be these wavelengths over here, the small ones, sort of all together.
Exponential, is that?
Yeah, basically once you get to about 6, there isn't much of a difference. So basically it could be infinite level. There's not much of a difference between 6 and the next one away. These were enough, basically up to 6 or 7 was enough to explain all the wavelengths that they could see at the time. So moving between the highest levels gave you infrared. Moving from the highest levels down to the second level is a bigger loss of energy. That gives you the visible light. So that would be the light in this part of the spectrum. Higher energy than infrared, not as high as ultraviolet. But that's the light we could see. And you see they come in a packet, basically. Those wavelengths are sort of all stuck together because the energies are fairly similar. And then the biggest jump from the highest wavelengths all the way back to the ground state are big changes in energy. Those give you the ultraviolet or the UV. Those are high energy wavelengths. So that tells you that's a big distance that the electron fell. And that gives you this series of wavelengths here. So basically what they saw was these patterns of wavelengths sort of all grouped together. There'd be a group here in the ultraviolet, and then there'd be a group here in the visible, and then there'd be a group down here in the ultraviolet, all sort of packed together. And Bohr explained it by the distances from the nucleus.
Excuse me.
Yes.
How did he get H atom instead of hydrogen gas?
How did
Bohr get just an hydrogen atom?
Oh, it's easy. Yeah, you just do a reaction and collect hydrogen gas.
Okay.
Yeah, chemists are been able to do that for a long, long time.
Okay.
Yeah, so you're wondering how we got pure hydrogen? Yeah, it's really essential you have very pure hydrogen, but that's not a problem to do.
Okay.
You just do a reaction where it releases only hydrogen gas and just collect the gas and you're good to go.
Okay.
So another Swedish scientist named Rydberg did basically just mathematics on the same thing. And his work showed that, this Bohr's theory, it kind of makes sense. Now, don't worry too much about the equation here. What I want you to focus on is that when Rydberg was looking at all the different wavelengths, he could explain all of them with whole numbers. That's the key to the whole thing. So he would derive this constant that, I don't know, someone came up with the idea to name it the Rydberg constant. Well, there you go. But the key, really what I want you to remember about this is that you could use whole numbers to describe each and every one of these lines. And that gave real credence to Bohr's idea that there are whole number levels that these electrons are in. Everything made sense. It's like, we could now map all of these lines and relate them back to whole numbers. Oh my God, this is genius. This is going to work for everything. Not so fast, because what happens is this. So once we start looking at basically the other elements, so they started with hydrogen because, well, it's the simplest. It's only got one proton and one electron. Let's not get too deep into this. And so we can describe hydrogen perfectly. We can describe it down to the last wavelength, up to like 4 or 5 significant digits. It's going to be that easy for all the other ones too, right? Now, unfortunately, any other element you put in there, even helium, any other element you put in there doesn't work anymore. These equations completely break down. I mean, look at neon, for instance. Just look at neon's the third one down. And look how complex that line is compared to what hydrogen was. It's far more complex. And neon's got 10 electrons. So we're not even dealing with, with like really big elements. Neon's not that big. It's only got 10. But it's the complexity of it is so vastly much more than hydrogen that Rydberg's equation didn't work anymore. Bohr's explanation didn't work anymore, and people were freaking out. So like it was around 1913 that Bohr published his analysis. And so it took for about 10 years afterwards, people were just scratching their heads going, oh, damn it. What do we do now? I mean, if it doesn't work for hydrogen, maybe it doesn't work for anything else. Maybe Bohr wasn't right after all. Maybe there's something else going on, but what could it be? And it took a while for people to start thinking in a completely different way. Because the way Bohr was thinking about it, he was thinking about the nucleus, and for hydrogen, that's a proton. The proton is a particle. The electron is a particle, and we're going to treat them like particles. They're just going to move around, and we're going to treat them just like Newton would have. In fact, that he used Newton's equations to figure out the energy differences, and so that all worked beautifully. But at the time, in the late teens and early 20s, I mean, there was a revolution in science. There's a revolution in a lot of different things. You probably are aware. And one of the revolutions that came along was, what if these things weren't particles? What if they were waves? And it's Schrodinger who came up with this idea that maybe Bohr's plan doesn't work for these more complex things because he's not thinking complexly in a sufficiently complex way. Maybe these aren't particles. Maybe they're waves. What if we treat them like waves? There was a lot of mathematics being done at the time about waves. And so Schrodinger went, well, if I treat these particles as waves and plug all these equations that we've been using for light waves, and then I treated electrons like light waves, I wonder if that would work. And it turns out it does. It turns out it does very well, actually. So since Bohr's theory worked for hydrogen, but for nothing else, Schrodinger was the one who had the breakthrough that came along and said, well, if we treat electrons as, whoops, let me go back. If we treat electrons as waves, maybe then we could have a better idea of how far they are from the nucleus and actually figure out where they are, rather than being just these discrete circles around the nucleus. Maybe they don't look like that. Maybe they have a more complex way of appearing. And so he came up with these wave equations that gave the energy levels of atoms that worked, not only for hydrogen, but for every other element that's been looked at so far. So this is his equation. So I want everyone to memorize this because it will be on the test in 2 weeks. What do you think? Think we'll be able to derive this equation from scratch? I know I won't. I sort of know what some of these signs are, but yeah, it's obviously this is beyond this particular class. But what I want you to take away from it, what these wave equations actually do is they tell you the probability of where a wave is going to be. That's basically all it is. Instead of with particles, we say this particle is here, this particle is here, and that's the way it is. We can measure it exactly. When you're dealing with something like this, that's just, insanely complex, what the difference really is, what it really comes down to with this particular equation, is that it gives you a probability of where the wave is. It's here. We can say it's approximately here. And we measure it, we can say it's approximately here. And that makes a big difference in measuring these things. Let me show you, let me give you an idea of what I'm talking about. So here is Schrodinger's wave equation for the first level. And so, as I mentioned, it doesn't give you a precise distance away from the nucleus. It gives you a probability. It gives you a probability of finding an electron from the nucleus. So here's the distance. So the further away we go. And then this is the probability going up. And so the maximum probability of finding the hydrogen electron is at 53 picometers away, pico being 10 to the minus 15. Yes. No, 12, sorry. Femto is minus 15. So that agrees exactly with how far Bohr said the electron was going to be. So that agreed perfectly. So, okay, so far so good. So remember that this is a probability. It's not precise. Anyone remember, who watched Breaking Bad? Some of you got to watch Breaking Bad, right?
I love it.
What was the name of Walter White's character?
Mr. White,
What did he call himself? What did he,
chemist.
no, what name did he give himself when he started making meth?
Oh, I forgot it.
Heisenberg?
Heisenberg. Heisenberg was the person who came up with the idea that with this probability, you can't measure both the speed of the electron and the location of the electron precisely. He came up with the Heisenberg uncertainty principle. And so that tells us that if we measure how far the electron is from the nucleus, we can't say precisely how fast it's moving. Or if we can measure precisely how fast the electron's moving, then we can't measure exactly how far away it is. There's a certain uncertainty in it. And that leads to the whole Schrodinger's cat that I showed you in the very beginning. There's always going to be some uncertainty when you're measuring these things. And you're not going to know what the certainty is until it's measured or observed. So basically, with the cat in the box, you don't know whether the cat is alive or it's dead until you open the box. Basically, it's both. Ooh, it's sort of this, it's in this spooky between world things. And the sort of, the electron is sort of similar. You don't know exactly where it is until you either measure how fast it's moving or how far away it is. And that's thanks to Heisenberg, actually figured out exactly the equation to figure that part out. But what I want you to take from this was that the very first level, and we call this 1s, and we'll talk about why it's S in a little while. The very, very first energy level for electrons looks like Bohr said it looked like. It's this distance away, and if we look at the shape, that's the other advantage that Schrodinger's equations gave us. Not only did it tell us how far the electron was going to be away from the nucleus, it told us what shape the orbit was going to be when you got there. So it gave us two really important pieces of information: how far away it is and what shape the orbits take when it gets there. And so for the very, very first level, the shape looks like this. Now again, these are probabilities. And what we're looking at here is that the closer we get to the nucleus, the higher the probability goes. And what does the shape look like? Well, it looks like a big sphere or a big circle, just like Bohr said it would. So, okay, this is my first electron. and it looks like Bohr says it does. Okay, so they agree. That's important too, whenever you're looking at a new scientific theory. A new scientific theory comes along, and if it doesn't explain everything that came before it, then it's not a very good theory, is it? If it could only explain new things, but it can't explain the things that came before, then no one's going to believe it. No one's going to give it any credence. But this theory agreed with Bohr's theory before it and explained new things to come after it. So that's why basically it's been accepted for 100 years. So this very first level, we know how far the electron is from the nucleus, and we know that the shape of it is a sphere. Okay, so far so good. That makes nothing too weird yet. What about the next ones further away? Well, if you plug those numbers into the wave equation, it tells you that the next level, and we're going to call that 2, okay, 2, also looks like a sphere, but a much bigger one. Okay, that makes sense. And the distance is right where Bohr said it was going to be. So again, it nailed everything that came before it and explained new things as well. So the highest probability of finding this electron in the second level was at 250 picometers, just where Bohr said it would be. What about the third level? Well, even bigger sphere this time. Now the highest probability is 680 picometers away, just where Bohr said it would be. And big sphere this time. Notice that the spheres are getting much bigger as we increase. The first one was around 50, and the second one is 250, and the third one is 680. So it's getting quite far away. These atoms are getting really, really, really big as we're adding more and more levels. But something else we'll see happens. It's not as simple as bigger and bigger spheres, because if it was, Bohr's theory would have worked for larger and larger atoms, but it doesn't. So Schrodinger showed that works for a single electron, just like Bohr said it would. But when we start adding more and more electrons, it doesn't work anymore. And so when we plug in the values into these wave equations, we find out that we can basically describe any electron with 4 numbers. And we're going to spend a lot of time on this. 4 numbers, basically an address. It's going to be like a zip code. These are going to be like the zip code for electrons. Zip code for electrons. Because you give a zip code that basically tells you what neighborhood, breaks down any neighborhood in the United States. Now these 4 numbers tells you exactly where an electron is. And it's unique for every single electron. So unlike a neighborhood, it tells you exactly what electron we're dealing with. So 4 numbers. The first tells you how far it is. And we're going to go over this quite a lot, so don't worry about it if you don't get it immediately. The first one, called n, tells you how far it is. Remember, we said n equals 1, n equals 2, n equals 3. That's fairly straightforward. How far away is it? And then the next one is going to be L. That tells you, okay, I know how far away is it. What shape is it? Because we're going to find out that these orbits have all kinds of really weird shapes. Some are very strange shapes. But what shape is it? The third one is going to be M. M to the L. That'll tell us where inside these weird shaped subshells. We're going to call this one the shell. That tells you how far away it is. The second one, we're going to describe that as a subshell, so inside the shell. The third one is going to be which orbital. And I'll explain what an orbital is. Basically, it's where an electron is inside the subshell. And then the fourth one is going to be, it's spinning. The electron's either going to be spinning clockwise or it's going to be spinning counterclockwise. That's basically the only two ways something can spin, right? This direction or in the other direction. Now, those are the four numbers, and no two electrons can have the same four numbers. They have to be different. So even if two electrons are in exactly the same place, one is going to be spinning clockwise, the other is going to be spinning counterclockwise. So even if they're in the same orbital, and we'll show that orbitals contain two electrons, even if they're in the same physical space, they have to have different spins so we can tell, so we can differentiate them. And we know that they're spinning. It's like someone made this crap up about them spinning, right? That's just to explain how we can tell them apart. No, we know that they're spinning because this spinning part explains magnetism, which is really cool. And we'll get to why some elements are magnetic and some elements aren't, just based on how their electrons are spinning. So that'll be cool when we get to that. So I'm just going to take a break for a sec and let's cool off. Anyone have any questions so far? We're going to get more into this, but I sort of want to just lay out generally what we're going to be doing. Again, is it too much for people too early in the morning?
So much in general times too, Professor.
It's so much for at any time. It'll start to make sense after 5 or 6 years of doing this, I swear. That's all it takes.
I'll do my best for 5 and see how it's going to work from there.
Cool. Yeah, so basically, we're going to get an address for every electron. Now, what I want to show you is the shell we sort of know already. Bohr came up with the shell. The shell is basically that first, the levels he talked about in a big circle, right? The big sphere around. That's just the ship. That's the first one. That's the shell. That works. That's still there. But there's a lot of things going on inside each shell that we're going to learn about. It's the subshells inside and the orbitals inside the subshell. That's what we're really going to start learning about. So this is how we basically the atom is organized as far as we can tell. So we have our nucleus, and then as we move away from the nucleus for larger and larger shells, we have room for more and more electrons in each one. So the first one has 2. So when n equals 1, there's room for 2 electrons there. So if you have 1 electron, that's hydrogen. If you have 2 electrons, what's that?
Helium.
Helium. And then that's it. Those are the only 2 elements that just have the single ground state shell. That's it. There's only 2. And then we move to the next shell. And if you remember from the periodic table, and I'll keep coming back to this, the periodic table, how it was organized, as we went down, we had a different grouping across each one, right? As we added, first we had hydrogen on one side and helium on the other side. And then we moved down, and then there was 8 elements in the second row. And then there was 18 elements in the third row. And then there was 18 elements in the fourth row. And then it got larger and larger. This explains where that comes from. So there's only 2 in the very first row. And then there's more and more and more as we add more and more shells. Okay, and we'll show you how this works. Hopefully, it'll make some sense. So the first quantum number, we call this the principal. Now, again, where they get these names, someone came up with these names. What I really want you to remember is shell, subshell, orbital, spin. That's really the important thing to remember. So the first number, n, tells you how far away. That's Bohr's shell. That's Bohr's sphere. How far away is it? The second one, it's called angular momentum. It's the subshell. Let's just call this the subshell. First one is the shell. Second one is the subshell. It gives you the shape of the subshell inside this one, inside the shell. And we'll see as we add shells, we add more of these because there's more space, there's more room for electrons. We notice when we start looking at the distances, as we got further and further, they got really far away. Like there was 50 picometers, and there was about 250, then there was like 700. So as we get further and further away, there's a lot more room to stuff electrons in because there's a lot more space. And these are what we're going to be putting those electrons in. And they're going to have all different kinds of crazy shapes, as we'll see. Now this number, L, will go from N, basically 0 to N minus 1. So if N is 2, then L can be either 0 or 1. And that tells you what the different shapes are. L equals 0 is one shape that we'll see. L equals 1 has a different shape.
Excuse me.
Yes.
Why is n minus 1? I mean, why it cannot start from 1?
Oh, I'll show you.
Okay.
Yeah, there's a reason. There's a reason for all this. And actually, the next page shows you the reason. So, N and L. Shell, subshell. Next one is the orbital. Now, the orbitals are the actual physical locations where the electrons are. And this is called, now this is really messed up. It's called the magnetic quantum number, even though it has nothing to do with magnetism, which is kind of stupid. The spin has something to do with magnetism. That's why it's a little confusing. And that's why I prefer to call it the orbital. Now, the orbital has values ranging from whatever L was, minus L, through to 0 out to plus L. So if L equals 1, then the magnetic number can either be minus 1, 0, or plus 1. And we always put the plus in there. If L equals 2, then M can be minus 2, minus 1, 0, plus 1, plus 2. And this is really helpful because it always tells us how many orbitals there are inside any particular subshell. We don't have to memorize it if we can't memorize it. We can automatically figure it out. If L equals 0, then M equals 1. There's only one place for it to go. 0. That's it. That's the only thing. Sorry. Then M would be 0 as well because there's no minus 0 and plus 0. So it can only be 0. Okay. And then finally the spin, well, it's either clockwise or counterclockwise. And we call clockwise plus 1/2 and counterclockwise minus 1/2. And that's it. So they're all whole numbers until we get to spin. And that's why they sort of gave this a non-whole number, so we wouldn't confuse them with any of the others. So spin is either plus 1/2 when it's spinning clockwise, minus 1/2 when it's spinning counterclockwise. Okay? So where do these, let's have a look at where these come from, or what these different shapes are. So each shell, remember, as we go further away, the spherical shape, that's the shell, can hold 2, because there's 2 electrons in each orbital, times whatever the shell is squared. So the first one, so if n equals 1, it can hold 2 times 1 squared equals 2. So there's only room for 2 electrons. If we're in the second shell, then we square that 2, multiply it by 2, and there's room for 8. When we get to the third level, now 3, we square that, multiply that by 2, and we get 18. And then 4, square 4, multiply that by 2, we get 32. And really 32 is like the most we need, basically because this will describe for us all the elements there are. There may be bigger elements with that will someday come along that have more electrons in their shells, but this explains all the ones we have so far. And so we max out at 32 because we don't really need any more. And this explains everything we have to this point. So once we get past 4, 5, 6, 7, they all have 32 in them. And that's more than enough electrons to describe even the biggest element, okay? So subshells and orbitals. What the hell's going on with the, what is a subshell? So each shell, and remember, this is the spherical shell that we sort of be relatively familiar with, has exactly that same number of subshells. So n equals 1, there's 1 subshell in it. N equals 2, 2 subshells in it. N equals 3, take a guess how many subshells that has in it. 3, right? Up to 4. And these are what we call the different subshells. So you're probably familiar with S already, because S is the spherical shell that Bohr predicted. So that's the simplest one. And so and that's called S. You'd think it would be called S for spherical, but no. It has to have a more complex reason for calling it that. The next is called P. That's the second type of orbital. So at n equals 2, the next level further away from the nucleus, now we have 2 subshells, S and P. When we get to 3, so this far away, and now this far away, the third level away, now we have 3 subshells present. We have S, P, now we have a new one called D. And then when we get to the 4th level, now we have 4 subshells, S, P, D, and the new one called F. And the energies for each one, F is the highest, so this is the highest energy. D is the next, and then P, and then S. S is always the lowest energy subshell. And it's important to know this because as we build bigger and bigger atoms, we add electrons to higher and higher energy levels. So every time we add a proton and an electron, when we add a new electron, it goes to a slightly higher energy state. So each electron has a slightly higher energy state than the last one. Little higher, little higher, little higher. And so each subshell, these S, P, D, and F, has individual places where you can put electrons, and we call these orbitals. So shell, how far away from the nucleus is it? Subshell, what shape are we going to find these electrons taking up? Orbitals, where in this shape that we're going to be talking about are the electrons? Where exactly are they inside the subshell? And then finally, what spin is it? So orbitals in the s subshell, well, we just call them s orbitals. P orbitals, d orbitals, f orbitals. It just tells you where the electrons are. And each subshell has a very specific number of orbitals, and that comes from the third quantum number. Tells you, it's the orbital quantum number. It tells you how many there are. And remember, that is minus L to plus L. So the subshell number is M. That tells you which subshell it is. Or sorry, is L. That tells you which subshell it is. And then this tells you which orbital inside it is. So if it is P, for instance, P, that's L equals 1. S is 0, P is 1, D is 2, and F is 3. 0, 1, 2, 3. And so if I have a P subshell, how many orbitals does it have? Well, its number is 1, and so it goes from minus 1 to 0 to plus 1. Well, how many is that? 1, 2, 3. It's 3 orbitals. Okay, and we're going to use this over and over again to figure out how many, basically, where are all these electrons going. So S, 1 orbital. Because S, the value for S is 0. So there's only one place for those orbitals to go. 0. P, remember, its number was 1, so it could be minus 1, 0, or plus 1. D's number is 2, so it can be minus 2, minus 1, 0, plus 1, plus 2. That's 5 locations. F equals 3. So if it equals 3, where could the electron be? Well, it can be at minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. That's 1, 2, 3, 4, 5, 6, 7 places where it can be. And so there's 7 orbitals. Now, on top of that, it also tells you what shapes they are. And like I said, there's going to be some really twisted shapes coming up. So strap in. S is just a basic spherical orbital. That we can picture. That makes sense. P is a 2-lobed orbital. Basically, it looks like this, where the electron can be here or here along an axis. Now, I'll show you what these look like. P orbitals look pretty cool. And we'll learn when we do our section, our next section is going to be bonding. The p orbital, the shape of the p orbital describes very well how we form double bonds. And so we'll get into that as well. Now, an orbital can have no electrons in it. You can have 1 electron in it or 2 electrons in it, but never more than 2. So there's either 0, 1, or 2 electrons in it. There's only room for 2. And if there's 2 electrons in an orbital, they have to have the last number of the address. Since they're in exactly the same house, they have to have different spins. So the very last quantum number has to be different, because remember, every electron has to have a different set of quantum numbers. So even if they're in the exact same location, they have to be different. One spinning one way, one spinning the other way. Okay? Let's have a look and see what these look like, because some of these look really cool. So if you're wondering where the letters come from, they actually come from the light that come off from each one of these, from each atom. When they look at the spectrum that the excited atoms give off. S stands for the S stands for the sharp lines. S stands for the sharp lines. So that has just one orbital with 2 electrons. P stands for the principal lines. So I guess the next in intensity next to the sharp. So P for principal. Now there's 3 orbitals in the principal subshell, and so there's room for 6 electrons there. Each subshell has a different number of orbitals. Each orbital has room for only 2 electrons. The next subshell, D, stands for diffuse. So I guess those particular lines were very, diffuse. They were like fuzzier, harder to measure accurately. Those subshells have 5 orbitals or room for 10 electrons. And then finally, F stood for fundamental. Now, where fundamental comes from, I don't know. Fundamental must be, those were the last ones to find. Fundamentally, they were the hardest ones to get. But I find I can't remember sharp, principal, diffuse, and fundamental. So what I like to say is that special puppies deserve food. I have 2 puppies. They're both very special, and they deserve food. So that's how I remember it. Special puppies deserve food. You can use whatever mnemonic device you want, but that's one that works for me, because sharp, principal, diffuse, and fundamental don't really stick in my brain very well. But S, P, D, and F, we're going to be using that over and over and over again. So figure out some way to memorize the order that is S, P, D, and F, because we're going to be doing it over and over and over again. If you want to use puppies, works for me. So these are what the shapes of these different subshells look like. So the L, the second number, remember M is the N is the first number. That tells you how far away from the nucleus. L tells you where inside that shell are the electrons. What shape determines where they're going to be. So this gives you the shape. S, P, D, and F. Hey, shh. S, P, D, and F have fundamentally different shapes. And so this L, as I mentioned before, can have values from -n to +n. That'll tell you exactly how many different orbitals there are. So S orbitals are simple, just like the very first slide we looked at with Schrodinger's equation. The very simplest orbital is a sphere. And he agreed, his wave equations agreed with Bohr, who said that it was a sphere. Said, yeah, it's a sphere, makes sense. That's the simplest shape we can think of is a sphere. Equal distance from the nucleus all the way around. It can't be a cube or something like that. So, but P orbitals look different. They look like balloons with a knot in the middle. They look like this, as I showed you before. So there's our axis going through it, and we have equal density on one side, equal density on the other side. And they come in 3 dimensions. They come up and down, side to side, and in and out. So it's a three-dimensional shape. D orbitals look like 4 balloons tied together with knots. And F orbitals look like 8 balloons. Like F orbitals is just crazy business. So each one of these subshells gets more and more crazy shapes. Don't worry about the shapes too much. P orbitals are important to remember the shapes, but D and F orbitals, their shapes are so insane. They're kind of hard to remember. But S is a sphere. Okay, got that. And P looks like a balloon. or two balloons tied together with a knot in the middle. That's going to be important later on, as I said, when we're dealing with double bonds and triple bonds. That will come back into play. D and F, they just have crazy shapes. So I'll show you what they look like. But the first two shapes are going to be important to remember because they fundamentally are important to the way we think of chemistry. So, S orbital, simplest one, S, sphere. Lowest energy. At any particular shell, this is the lowest energy subshell. So this is the first place. So as we're adding electrons, as we go from hydrogen to helium to boron to beryllium, so on, as we keep adding electrons, we go to the lowest energy. So we start in 1s, and we put our 2 electrons in there. And then we go to 2s, and we put our 2 electrons in there. And then 2p, because that's the next highest. So S is the lowest energy state in any particular shell. So we always start with S. S is the very first place we put electrons when we add a new shell. So like hydrogen, we would describe that as 1s, and it has 1 electron there. This is the electron configuration of hydrogen, and I'll talk about that a little bit later. This basically tells you where all the electrons are in a particular element. Hydrogen's only got the 1, so it's in the first energy level, first shell, in an S subshell, and there's 1 of them. Then we move to 2. That would be 1s2. That's helium. Still in the 1s, still in level 1, because we've only got 2 electrons. These are all ground. These are all ground state. So they're not excited. These are the ground state. We could say electron configuration. So first shell, S subshell. How many are there? 2. And then when we add our third electron, would be 1s, 2, 2s, 1. So these are where the first 2 electrons are. Where's the next one? There's no more room in the first shell because there's only the S subshell, and the S subshell only has room for 2 electrons. That's it. So we got to move up to the next shell. The next shell, where's the very first place we put electrons? Well, that would be the S subshell. And how many have we put in there? 1. So that would be our total of 3 electrons. And then the next one would be 1s2, 2s2. That would be 4 electrons. And so on and so on. The next one would go into P because that is the next highest level subshell in the second shell, and so on and so on. Okay, but we're going to get to that in a little while. But that's basically how we fill electrons as we go forward. This is the lowest level, in lowest subshell inside any shell, the S orbital, and it's a sphere. Sort of makes sense of that. Doesn't have any nodes. Anyone tell me what a node is?
NODE? No.
Yes, a node. NODE.
Is it in waves that a node is
What do we find at a node?
the place then no energy is emitted? And
Right. Well, it's a place where we won't find anything. And remember, these are probabilities. This is what the probability looks like that we will find the electron an equal distance away from the nucleus inside this spherical shape. So you can see that anywhere inside this particular spherical shape, we have equal probability of finding that electron. So there's a node is where there's no probability of finding it. So we'll see that when we have a p subshell with this shape, there's probability here, and there's probability here, and there's no probability in the middle. That's where the nucleus is. So there's no probability of finding an electron in the p subshell near the nucleus. It's going to be away from the nucleus. Okay, so let's have a look and see what that shape looks like. So each principal, each shell above the first one has p subshell in it. It has one p subshell in it. And each subshell has 3 orbitals. And this is the address for those 3 orbitals. -1, 0, and +1. That's the address for each one of the 3. Each one of those orbitals points along a different axis, as I showed you before. So x, side to side, y, up and down, and z, z coming in and out. So the three-dimensional axes. It's the second lowest energy level, second lowest energy subshell. S is the lowest, P is a little bit higher, D is a little bit higher, and F is a little bit higher than that. Excuse me. It has 2 lobes, as I showed you before, one here and one there, and it has a node where there's no probability of finding the electron there. So it's not going to be there. It's going to be over here, or it's going to be over here. It's not going to be in the middle, okay? What does that look like? Now, this is the other one I sort of want you to pay attention to the shape, because the shape is going to be very important later on. So as you can see, it's sort of like the, 2 balloons tied together in the middle. Yes.
And how to distinguish the 2 p orbitals and 1 d orbital?
Sorry?
How do you distinguish?
They're different shapes. We haven't got to the D yet.
Okay. Okay.
Yeah. So this is, the p orbitals are fairly simple to remember. They're just the 2 balloons tied together in the middle. But this is what I want you to see, is that they're at 90-degree angles from each other. Now, this is something that when we talk about molecular shapes, will be really, really important. Remember, electrons repel each other. They don't want to be close to each other. They repel each other. And so if we have 3 different pairs of electrons traveling together, what's the furthest away from each other they can get? Well, 90-degree angles. Here we have a pair here along the x-axis. This is the x-axis here. Y, so this axis going back and forth, and then Z here. That's as far away from each other as they can get because they repel each other. So this is as far away as they can get away from each other without moving back closer together again. So this shape, and then this shape. So this would be our X, this would be our Y, and then the Z would be forwards and backwards. So far away from each other, each one of them can possibly be. And we call them PX, PY, and PZ, or -1, 0, +1. That's where the addresses come from. So -1 would be these, 0 would be these, and +1 would be these. Okay? Any questions so far?
Well, Professor, can you repeat where the
I don't
numbers
even
come
know
from
the
again?
question.
What was that? Can I repeat the numbers? Which numbers?
Where the numbers come from?
Oh, the numbers. Yes, the numbers come from. So N tells you which shell, how far away. So 1, 2, 3, whatever. Next is L, and that tells you which subshell we're dealing with, S, P, D, or F. And those numbers are 0, 1, 2, or 3. So the first one is 1, 2, 3, 4, 5, 6, 7. L can only have 4 values, 0, 1, 2, 3, for S, P, D, and F. 0, 1, 2, 3. Now, M to the L tells us where is that electron. So we know how far away from the nucleus it is with N. L tells us which subshell it's in. But M to the L tells us where, which part of the subshell. Is it this one, P to the X? Is it P to the Y? Or P to the Z? Which one is it? We don't know which one it is. So M to the L tells us that. So since P has L equals 1, there's 3 different places for it to be. -1, 0, +1. And this is -1. This one is 0. And this one is +1. So it tells us exactly where inside those balloon shapes are we going to find that electron. Okay? This isn't going to be the last time we talk about this. So if it's not sinking in yet, don't worry about it. Okay? I'll just do one more and we'll call it a day. So that's P. These shapes I want you to remember. Like I said before, it's going to be really important later on when we're talking about single bonds versus double versus triple bonds. We'll find out that it's p orbitals that are involved with making double bonds and triple bonds. It's all due to the p orbitals. And because the p orbitals have these particular shapes, it explains how double and triple bonds are oriented. That's why this is so beautiful, because it explains so much other than just the periodic table. It also explains a lot of bonding we look at. So before we go, I just want you to look at something a little more trippy, and that's the d orbitals. D subshell. D subshell with 5 d orbitals inside. So n equals 2, or L equals 2 for D. So that means that there's now 5 different places it can be. -2, -1, 0, +1, +2. That's 5 places. 5 orbitals. That's what that means. Now, these have 4 lobes. They look like 4 balloons tied together rather than 2. And the 5th one is a toroid. Don't even ask me to explain that one. But 4 of them kind of make sense, and then the 5th one is a really weird shape. Let's have a look at what that one looks like. So the first 4 kind of make sense because they sort of look like p orbitals, only sort of split in half. So we have 4, 1, 2, 3, 4, along an XY basic two-dimensional shape. And then the next one, a YZ, and then an XZ. So these 4 kind of make sense, laying flat in different orientations. But then this last one has this shape, where it sort of looks like a p orbital with a donut in the middle. Now again, these wave equations get crazier and crazier the larger these subshells get. But those are the 5. So there's room for 2 electrons here. So -2, -1, 0, +1, +2. Those are the 5 places a pair of electrons can be. Now remember, each orbital has room for 2 electrons. So there's a total of 2, 4, 6, 8, 10. 10 electrons. And we'll see the d orbitals total have 10 electrons in them. So then we'll do F next. F makes this look like child's play. F is even super weird, but you don't really need to know the shapes of D and F. They're way out there. S, sphere. P, balloons tied together. Those are the two to remember because we're going to keep coming back to them over and over and over. Okay, so I'm going to leave it there, let it sort of sink in for a while. Well, don't worry if it's not all, we haven't figured it all out yet. I haven't figured it out either. And remember, physicists don't understand this either. They invented this crap. So really the takeaway lesson is just sort of try and remember the numbers, because the numbers, when we try and relate this back to the periodic table, you'll see it's all related. And then hopefully some sort of light will go on at that point.
Excuse me.
Yes.
Can you go back to the density, the page with the graph, the possibility?
Going the wrong way. These?
No. Go. Yeah. This one.
Mhm.
What is probability of density mean?
So with classical physics, we would define exactly where a particle was. We'd say that the electron is this distance from the nucleus, and we would measure it precisely. But now that we're dealing with waves, there is going to be some uncertainty of the measurement of exactly where that wave is going to be. And so instead of a definite measurement, we get a probability of where that wave is going to be. And so we use the wave equations that Schrodinger gave to figure out the probability of where that electron is going to be. And this electron in the 2s, that electron in the 2s orbital, 2s subshell, we plug that in. Its most likely place to be is 250 picometers.
Oh, okay.
Yeah, so that's basically, this is the equation. And then in order to figure out the actual density, we solve for that equation and we get this line down here. So there's some small probability that it's in the first level. There's a slightly higher probability it's in the second, but the highest probability is it's in the third. And so, and that distance corresponds exactly to what Bohr said it was going to be. And so the two different theories agreed on these measurements. That's how it was thought that, oh, Schrodinger must be onto something here because this all makes sense. It all explains what was seen before. It's only they start to blow people's minds when you start talking about 8-lobed balloons and everything, that you start to lose people. But this part made sense. Okay, so just remember Heisenberg, remember Walter White's hat, that there's always uncertainty in these measurements. So that's why we have all these weird shapes, because we can't say exactly where the electron is, but we know that there's a high probability that it's inside one of those shapes. So we're always going to be dealing with probabilities here. That's the difference between particles and waves. Particles, we know where they are. Waves, we know with some probability where they are. Okay?
I still don't get why the total radial probability comes from 0, but the density doesn't come from 0.
Oh,
Like
so,
the graph,
yes.
from 0 for
Well, if you're asking me to explain Schrodinger's wave equations, that's a little beyond my pay grade. But basically, this is this is an equation, and this is the solution to that equation. So don't get too hung up on, because we actually want the solution to the equation. We're not so much interested in the equation itself. We're interested in the solution to it.
Okay.
Yeah. Okay.
Mm-hmm.
All right. So, gone a little bit over. So, my group, I will see you at 1:10, right? 1:10. I'm gonna show up at 1:15 like I always do because I'm an idiot. But I'll try and make it there at 1:10. So we're going to be doing titrations and our old friend stoichiometry. But mostly you're going to be learning about how to do titrations today. Okay. So if there aren't any other questions, I will see you then.
Okay.
All right.
Oh,
Bye-bye.
Professor,
Oh, yes.
for the exams, are we going to be tested on what happens in the labs?
No, that's separate. That's a really good question. That's a separate exam. We'll be having a lab exam probably the week after that. Yeah, because we have I believe we have 3 midterms and either 2 or 3 lab exams. So the lab exam will be strictly based on theories and practices from the labs. And so there's going to be 2 different lab exams, one for my group and then one for AJ's group. Because we're doing different labs. So there'll be two different tests, hopefully at the same time.
So we're not going to be required to know the concepts for the labs going to be separate. Right?
Well, I mean, the stuff we're doing in the lab hopefully is based on what we're learning in class. But I mean, you'll get questions on the lab exam about like specific practices. In the lecture exam, you'll be getting like questions more about theories. But I mean, but in both you'll be doing a lot of calculation. But you'll be asked more about how you do the labs. What did you learn in the labs? What's the source of error in the lab? That's an important one. That's that sort of thing.
Okay, thank you.
Okay. All right. Really good question. I totally forgot about that. All right. We will see you soon.